Hi, I'm Marie-Cécile, professor at the University of Alberta in experimental particle physics to detect dark matter of our universe. I am working with my colleagues Jan Doctor to integrate particle physics activity for high school students, but also resources with a broad range of materials for teachers. Our goal is to incorporate existing elements with new ways of introducing students to physics concepts that underlie the data measurement of a real detector of dark matter and investigation by doing their own analysis. We are also working on building demonstrators of dark matter detectors that can be used in class for them to manipulate and extract data from the detector, but also as a support in their understanding and learning. Before presenting you the activities we have put in place, I will give you an overview of the particle physics world and shedding light on dark matter. So particle physics is the study of the fundamental constituent of the matter and their interactions. There is a strong connection between the small scales and also the large scales because everything is connected. For example, by using the accelerators, such as the Large Hadron Collider, it is like using a microscope in order to study fundamental constituents on the smallest scale. At the same time, since we need very high energy by using this accelerator of particles, it is the same as using a telescope and probe the first instant when our universe was born, which means that the research and fundamental questions on the smallest and largest scales are closely related. So let's first have a tour towards the infinitely small. But that means the study of subatomic physics. And we have in subatomic physics the standard model. The standard model is similar to a dictionary of all particles we have detected, and it includes fundamental particles of matter plus their antiparticles. So we name them fermions. So as you can see here, fermions are particles of matter, and if we zoom in, we have the atoms where we have some subcategory of fermions which are leptons, such as the electron. But if we zoom in even more, we have the nucleus. And then even more, we have the protons and neutrons that are composed of quarks. So the fermions are the family of particles of the matter. But we have other particles. We have the particles of interaction, and they are named bosons. Bosons, and they are the mediators of the fundamental forces that we have in nature. For example, photons are the mediator of the electromagnetic interaction. We have WZ bosons, who are the mediator of the weak interaction. And finally, gluons, who are the mediator of the strong interactions. So all of what we know would not have been possible without accelerators, because in order to detect these fundamental particles, we need an extremely high amount of energy. So paradoxically, we can say that the world of the infinitely small is also called the world of high energy. Very strong connection between those two, and all particles have a mass given by their interaction with the Higgs. So we have also the Higgs boson, and that was discovered about 10 years ago. And as you can see, we need to detect those particles. We need a huge detector, the Large Hadron Collider, which detect the collision of two particles, proton, that we are accelerating through this 27 kilometer. And we are looking at the product of this interaction at the Earth of this Large Hadron Collider. So as you can see, to detect those particles of high energy, we need high energy as well accelerators. And this is where the connection is with the infinitely large scales, because by using high energy, we are also going back to time with the Big Bang. We are reaching energy that was there at the first instant of our universe. So let's have a deeper look of the connection between the world of infinitely large scale of our universe. So for that, we have here a journey to the infinitely large. And as I said, that means going back in time and going back to the Big Bang. The Big Bang is our current best theory in the way of how our universe began. And we don't know really well what happened during the Big Bang, but what we know is that we had an extremely high temperature, which is connected to extremely high energy. And as much as the universe cooled down, we have the formation of fundamental particles, such as electron, quarks, etc. And you can see that it's only between 100 seconds and 1 billion years old of our universe that we have the formation of hydrogen atoms and helium. So all of this temperature, which is very high, is connected to a special energy as well to be able to detect those molecules and particles. So finally, we had, after 1 billion years, the galaxy formation, star formation, and solar planetary system to arrive in our day, 15 billion years old, where the temperature is very low compared to what we had before. And what we do is now, with the universe as it is, we can determine what is the amount of visible matter, of the energy content of our universe. And what we observe is that, in fact, we had only a tiny amount of what we know about standard model particles, tiny amount of visible matter when we are exploring the stars, what they are composed, and especially when we are looking at galaxy clusters and also the light in our universe. So this is a nice introduction for, in fact, dark matter, because it is from astronomical and cosmological observation that we found that one of the largest mass of our universe is in fact dark. So let's have a look in the history. In fact, the first evidence of dark matter was made by Fritz Zwicky in 1933. In fact, he studied the Coma galaxy cluster. And what he found that the mass he calculated from the velocity of the star was 400 times more than the mass expected from the luminosity that he can see. So he was surprised to find that if this estimate were correct, at the speed at which the galaxies were moving, they should have flown apart. So due to that, he postulates that it can be only a substantial amount of matter, non-emitting light, that must exist to allow the system to be gravitationally bound. And in fact, it's 40 years later that finally we said, okay, there is dark matter, thanks to Vera Rubin, an astronomer who measured the rotational curves of spiral galaxy. So she was studying this spiral galaxy here. And in the spiral galaxy, a star rotating around the galaxy feels two forces. It feels the gravitational force that band everything together, and feels also the centripetal force because the spiral galaxy is turning. And at the equilibrium, the two forces are equal. So we have the centripetal force here, and here we have the gravitational force. Thanks to this formula, we can extract the speed, rotational speed of the stars within the galaxy. And as you can see here, it's just we isolate the rotational speed, and we get G, which is the universal gravitation constant, the mass of the stars at a certain radius r over the radius where the stars are, and everything root square. So this is what we should obtain. And what she found is her observation disagreed with the gravitational laws. If we look at here, this nice diagram, we have the spiral galaxy here and the radius from the center of the galaxy. And you can see we can go very large radius. And here is the velocity. So what we see is that what we should expect is, since at large radius there is no more stars, no more actually mass that we can see at least, we should also have less mass and also higher radius. So that means if we look at this formula, we should have the rotational speed decreasing with radius. But what we are actually seeing and observing is that this velocity, in fact, is increasing. Is it increasing? And the only way to explain what happened here is by increasing the mass. So that means we need to explain those observations a huge amount of matter, of mass, which is not visible around the galaxy. So that was really like the starting point of where we should find the dark matter of our universe. And in fact, if we look at in terms of notion of the galaxy, this is what we have as a whole notion of galaxy. But if we could see dark matter, in fact, we should see a halo of dark matter. So thanks to all of this proof, in fact, we were able to reconstruct what is the energy content of our universe. And all the scientific were very surprised to see that 5% of our universe energy content, it's made of visible matter. It's made of electron, proton, everything that we know, wood, everything that we know is only 5% of our universe. And we have 27, about 27, it's dark matter. And even more, it's the dark energy with 70%. So let's concentrate on the dark matter. Dark matter, 27%, huge amount of mass in our universe. So what can be dark matter? Thanks to the astronomical and cosmological observation, we were able to build an identity card of what could be dark matter. And what is clear is that it's not a visible matter. It's not something that we know. It's not a particle of the standard model, not a fermion, not a boson. And since it's very heavy, it's what we name a cold dark matter. Cold dark matter means that the particles of dark matter are non-relativistic. So that means they don't have the speed of light. They have a much slower speed. So this is what we name cold dark matter. It's non-baryonic, so it's not composed of quarks. It's massive, 27% massive and stable. It's neutral, otherwise we would have detected via electromagnetism or, negative or positive charge, we would have detected. It's very weakly interacting because it's still, we didn't detect it yet. And it's also not a particle of the standard model. So that means it's really new physics. And one of the favorite candidates to date is the WIMP, weakly interacting massive particle. So the next thing we should ask is, okay, we have this particle, how can we detect it? So we can detect it directly. This is what we are building detectors to detect it directly. And what we are looking at is, in fact, the elastic scattering on nuclei. So that means experimentalists try to look for the recoil of the target nucleus. So we have a particle of dark matter interacting elastically with the target nucleus that we are using inside our detector. The dark matter diffuses in a certain way, but what we have left is the recoil, the nuclear recoil of the target nucleus. So it's really, if you look at as a pool table where you have the target here, and finally you do the elastic scattering and put this recoil here. So the WIMPs interact with the nucleus, and we can observe the interaction by detecting the nuclear recoil of the target nucleus. And just to give you an idea of the energy, because we said that it's a weakly interacting massive particle, so that means the recoil energy that we will have will be very, very low. But what is the order of magnitude? In fact, let's take the example of a grain of salt at 1 millimeter from the floor, and you let it fall. The force that it will touch the ground divided by 100 billions, this is what we try to detect. It's very, very low energy to detect. So that means we need hypersensitive detector to detect dark matter. And when you say hypersensitive detector, that means we can detect everything as well. So we want to detect a very rare event without being bothered by everything else, which we are always. But this is something I will talk about a little bit later. That are the main challenges we have. So just to give you an idea of which kind of technology we use to detect dark matter, in fact, here is a schematic of all possible signals that can be measured in direct detection experiment, depending on the technology in use. So this can be, for example, the production of heat, for example. You can have also by the direct ionization of target atom. So you detect the charge, and that can be as well by an excitation of the target nucleus, which disexcites, releasing scintillation photon. So you have the light. And all of these technologies are trying to detect dark matter. And the way that they are comparing between each other is by drawing the cross-section of this dark matter as a function of the mass of this dark matter. And when we say cross-section, that means what is the probability that the particle of dark matter interact with my detector. And this comparative plot, it's something like this here, where you have the cross-section here as a function of WIMP mass, and each of those lines correspond to different experiments depending of the results they are analyzing and data that they are analyzing, they are able to say that above this line here, I can exclude there is no dark matter, but everything below needs to be still discovered and explored. So here, depending of the detection technique, some of the detectors are very sensitive to what we name low WIMP masses, and some other detectors are sensitive to very low cross section. So finally, what do we need? What do we need to detect dark matter? In fact, the detection depends essentially of the WIMP mass that we don't know and the background around us. So what we have seen, the key point is that the recoil created by the WIMP is very, very low. So that means we need detector able to reach those low energy, and this is what we name low threshold detector. We know that it's a very weakly interacting massive particles, so that means the rate of this interaction is very low. And to increase the probability of detecting this rare event, we need to increase the volume of the detector. And finally, the background is the principal problem for all dark matter experiments. We need very high purity level, otherwise we will see all the radioactive decay from the material, and also everything above us, the muon-induced neutron, the gammas, the cosmic rays, all of this is a background for all dark matter experiments. So because we are constantly bombarded from cosmic rays, for example, all dark matter experiments are located to underground laboratories. So here I am presenting you today SNOLAB. SNOLAB in Canada, Ontario, in Sudbury, is really a unique underground laboratory for the detectors looking for a rare event. It's at 2 kilometers underground in a mine. So here you can see the picture of the laboratory above ground, so at the surface. Here you can see some of us going to the shaft, so to the elevator to go underground. And here you can see this very nice area, which are the laboratory. So we are building and installing those detectors here at 2 kilometers underground. And here I put a nice picture of the student crew underground 2 years ago to install a detector in the underground laboratory. So I would like to make a tour of this laboratory. So here at the surface, you have offices, you have conference room, and in this special building here, in fact, is where you are putting your minor gear and then go to the shaft to go to 2 kilometers underground, and you arrive here and you need to walk about 15 minutes to arrive to the entrance of the laboratory. And then at the entrance, you need to clean with the water hose here your boots, enter, and it's not finished because it's a clean room inside a mine. So you need to remove your clothes, take a shower, and put new clothes to be able to work underground. And here is the cafeteria where we are all meeting each other to eat, etc., before going back to work on the detector. So the galleria, so underground here looks like this, where you have here in green all the clean room laboratory, and as you can see, many detectors are installed underground to detect dark matter. They collect data that needs to be analyzed in order to know if dark matter has been detected or not. So one of these experiments is Picasso. Picasso, which collect years of data. We have a lot of signals as well, and that can be used by high school students to be analyzed. So this detector is in fact the project in Canada to search for supersymmetric objects, and it consists of superheated droplets of freon dispersed in a polymerized gel. So you can see you have an acrylic container with 9 piezoelectric sensors to record the sound, the signal created in the detector when a particle interacts with a superheated droplets. So superheated droplets means that it's liquid, but at the pressure and temperature condition, they should be gas. But since they are trapped in a gel, they are liquid. And what does it mean? In fact, that means that when a particle deposits enough energy in this liquid droplet, it creates a phase transition between liquid state to gas phase. So you can see in this nice diagram, here you have a droplet, and after the interaction, you have a bubble form. And once this bubble form, this creates in fact an acoustic sound that are recorded by the piezoelectric sensor. And you have here a clear signals. So what we have done with Ian is we have collected signals from Picasso detector where students can analyze the amplitude of the acoustic signal. So as an example here, we have real data that students can use for analyzing the data, the signals, and determine which kind of particle has interact with the detector. And also here is the signal amplitude, but they can also work with, for example, the Fourier transform, the frequencies of the signal. So Ian will present later on activities that we built for high school students, but also modules that we have created as well for teachers. The second experiment that we are working on as well to put available modules and activity for high school students and also teachers is the NewsG detector. So it's an active detector. Picasso is a detector that was there in the past. Now it's Pico detector and scintillating bubble chamber because it's a kind of bubble chamber. But NewsG is actually a real detector installed actually as well underground currently. Here is some picture of this detector and is a spherical proportional counter. So it's, in fact, it consists on a metallic vessel filled with a noble gas mixture. And in the middle, we have a high voltage sensor. So the active target is in fact a gas of neon hydrogen mixture, so a very low atomic mass to be able to probe very low mass whip. And the signal readout is by just a preamplifier. So how does it work? What we want to explain is, in fact, how the particle interact with the gas, and we create animation, and also we have calibration data with what the students can use to practice the research data analysis. And it's real also data used by the experiment. So here, for example, you have here a WIMP interacting with a gas molecule, and you have a primary ionization, where you have a creation of a lot of electrons that, because of the high voltage, they drift toward the sensor here. And at the vicinity of the sensor, what happens is that you have an amplification of the signal. And the signal formation is created by the current induced by the secondary ions here, drifting away from the anode. So here we have prepared a nice animation of how it works. You have an interaction of particles, the electrons drift toward the sensor. You see at the same time you have an induced current. And as much the ions are drifting, you can integrate the signal, and you have the charge here that you can collect all the signal and then analyze them for the data. So it's a real and nice project. And in fact, within my group, working in the lab, they would be very happy also to share their experience, research with the high school student, but also with teacher. So Ian will also present a list of students that are willing to go to high schools and talk about their experience, myself as well, for sure. And just to give you an overview of their activities, so they are working in the lab, but they are also very happy to be part of outreach activities as well during Dark Matter Day or the open house lab tour. So they are really very happy to share their research as well during those events. And for sure, also during the conference, we have a lot of activities all together when they can present their research, they win prize when they graduate, etc. So with Ian, what we want to create is really to enable strong connection between high school teachers, students, and the university, the research university, by giving the best resource, manpower, in order to incorporate particle physics in the curriculum of high school. So I will let now Ian presenting the different activities and resource accessible for teachers, but also for high school students. Thank you.
Okay, so I guess now we've come to my part. I'd like to thank Dr. Piro for that terrific introduction. I've had the privilege of working with her for about 6 months on this project, and it's really been an eye-opening experience for me as I've learned a lot more about particle physics. So I've put the link to where the resources that we've developed are currently being housed here, and hopefully everyone has a chance to look at them at some point. So I guess the first thing, rather than talk about the actual physics involved in dark matter, since Dr. Piro did such a wonderful job on that, I'm going to talk about how we can use these in teaching physics to high school students and what some of the curricular links are. Now, there's quite a few. Dark matter physics is quite complicated, and it draws on many different areas of physics, as you can see here, from momentum and energy. We could talk about electric and magnetic fields, half-lives, nuclear decay. There's really a wide range of applicable physics in our curriculum. The only struggle is that it does require a pretty good understanding of physics to start talking about dark matter and the knowledge we have for it. So we built the resources with that in mind, hopefully making the dark matter physics as understandable for teachers and students while still maintaining kind of a fidelity to the physics involved. So I'm going to walk through the 3 different modules or topics that we came up with and the various activities that go along with them. I'll present an overview of or snippets of some of the activities, and go into some detail on others. This won't go through all the activities we've developed because we just don't have time, but I've kind of highlighted areas I think are particularly applicable to Physics 20 and Physics 30. All the resources have been made in Microsoft Word, and where possible, we've kept all the animations and graphics as user-friendly as possible. So if there is something that you guys like that's not particularly, that's not designed exactly in the same way that you would use it, you can modify the resources or pull certain questions or graphics out and use them in your own notes or your own activities in ways that you would see fit. So the resources are organized around 3 different topics. The first one is the evidence for dark matter, and this is usually drawing on more astrophysical sources. So observations of the motion of stars and galaxies and galaxy clusters, and comparing that to what we see in the solar system. The second and third topics are specific to particular dark matter experiments or searches, Picasso and USG, as Marie-Cécile mentioned. And within each of these topics, there's a variety of different activities. Each of the activities focuses on a different concept, but they don't necessarily flow through one curriculum. So for instance, in the Picasso dark matter search, there's topics that cover energy and conservation of momentum, as well as piezoelectric detection, which is essentially spring constants and vibrations. So you might have to pick and choose what's applicable to the class you're teaching, but I'll walk you guys through each of the resources. Again, there's the website you can find the resources on is displayed here, as well as it'll be again put up at the end of the presentation. So the first topic is the evidence for dark matter, and this largely comes from astronomy. We look at the rotations of stars and galaxies and galaxy clusters, and we've also included some comparisons to our own solar system. Additionally, we've included as many animations, videos, and graphics as we can. So this video here on the left shows the expected appearance of a spiral galaxy rotating without dark matter, and then on the left one with dark matter. I've also gone to some great lengths to include as many nature of science and philosophy of science questions. So for instance, how do we know what we know? How reliable are the observations and evidence that we have? As well as some historical connections to researchers that have made these discoveries. So in the first topic, the second activity looks at orbital motion in our solar system. So there's a lot of really good connections here to things like Kepler's laws, circular motion, Newton's laws of universal gravity, and how we can use that knowledge to build a picture of what motion in our solar system looks like, and then eventually compare that to motion outside of our solar system. So again, in this activity, students are asked to use the information on orbital periods and radii of the planets, plot that information, and eventually use that graph, do some curve straightening, and use that graph to determine the mass of the sun. Okay. I consider this a fairly straightforward, if not somewhat graphically complicated question for Physics 20 students to do. Additionally, what we'll build on in activity 3 is doing something similar, but looking at the Triangulum galaxy. So again, in this activity, what I've had students do is plot the mass of the galaxy as a function of radius. So they're looking at the amount of light being produced by the galaxy and using that as a proxy for the amount of mass in the galaxy. And we know that's a fairly reliable estimate. Generally speaking, stars the mass of a star is proportional to the amount of light it emits. So the mass of a galaxy is proportional to the amount of luminous matter in the galaxy. And so students go through several different stages in this activity where they look at different size circles in the galaxy and figure out how much mass is being enclosed in that, and then plot that. So they should get kind of a mass for the enclosed light in the galaxy. And then they're comparing this, so we'll call this the brightness method for determining the mass of a galaxy. And then they'll compare this to a similar computation to what they did with the solar system, comparing the mass determined by the rotational velocity. Comparing these two methods shows that there's a difference in the mass, and students have to kind of explain what that difference is and then suggest possible reasons for it. Now, everything in red here is the solution key to all the problems. So in addition to the resources, the background information, the animations, and the images, we've included questions and solutions to the questions as well, with a fairly detailed key that teachers can rely on if they need to. So the second topic was looking at a particular dark matter detector, in this case Picasso. This is a bubble chamber, and this was a fairly new topic for me. I had to do a lot of research on my own to figure out how these actually worked. And so in some cases, there's a bit of a stretch to some of the physics 20 and 30 topics, but there's a lot of good connections to nuclear physics, conservation of energy, and conservation of momentum. So the resource starts with some background information on the detector. This is suitable both for students and teachers if you need a refresher on how, like me, on how these detectors worked, or if you want to provide some of this information to your students or use it in presentations to students. There's also animations, like the one on the left here is a bubble actually forming inside the detector. The second activity deals with calibrating Picasso. So because these detectors are so sensitive, it's very important that they're calibrated properly to remove any background signals. We were fortunate to have data from the original Picasso science run that was done in Snow Lab, and we were given, I think, about 80,000 data points. So it's not really practical for students to do this by hand. So this lesson actually scaffolds students through using software like Excel or Google Sheets to help them process large amounts of data fairly quickly. And it's all laid out for students in a fairly straightforward way to work through the use of Excel. And so what they're trying to do is take the amplitude of a background signal as well as a detected signal, and then figure out what the actual source of that signal was. So they'll take something like this, where you have a combined signal, something that Picasso would detect, and then a background signal that you could pick up from, let's say, placing an alpha source nearby. Students are then asked to process these signals using Excel, because with the number of data points involved, it wouldn't be practical to do it by hand, and process these signals to extract what the science signal or the dark matter signal might be. There's a lot of really good connections to physics 20 and physics 30 here in terms of things like wave interference, the analysis of data, understanding what background signals are, and nature science questions like that. And then eventually students are asked to extract a process signal like this and then interpret the graph, so to find out what the maximum amplitudes might be and where the signal starts, how long it lasts for, and do some other interpretations of the signal. The third activity we looked at deals with how the detector actually picks up the signal. This is using piezoelectric detection. So there's piezoelectric sensors. They are sensors that vibrate when an acoustic signal hits them, and that vibration produces an electrical signal that we can measure. The piezoelectric crystals can actually be modeled fairly accurately as a vibrating spring. And so there's some good connections there to physics 20 and spring constants and simple harmonic motion. And so in this activity, there's several good questions that students have to look at using frequency, spring constants, and vibrational mechanics. As well, like I said, there's some good animations here that we've included where you can see how piezoelectric crystals would actually work. The fourth activity deals with the elastic scattering that happens inside the detector. So when a dark matter particle hits a nucleus, in this case of fluorine, it recoils and causes the nucleus to recoil as well. Lots of good connections here to conservation of energy, conservation of momentum, charge, elastic scattering. And so in addition, there's a couple videos that we've made, animations that'll show how this actually happens. And some questions that deal in some detail with 2D momentum collisions and extracting what the original dark matter momentum would be. So these questions go into quite a bit of detail in the physics 30 unit. In addition, there's also some good connections here to things like atomic mass units, mass in electron volts over c squared. And then this will bring us to our third topic on NUSG. So NUSG is a new experiment with spheres, gases. These are, I think Marie-Cécile mentioned, these are what's called proportional counters. They're very similar in operation to Geiger counters, just with a lower potential difference. Again, I think like most physics teachers, this is something that I would need a fair bit of background information on if I was going to use in my classroom. And so we provided all that. I spent many hours taking some of the physics involved in this and structuring it in a way that's accessible to students as well as teachers if you guys want to incorporate some of this into your lessons. So there's good graphics that we've linked back to original sources, as well as background on the operation and the materials that are used in the detector. So the first NUSG activity deals with calibration. And just like Picasso, because the signal from dark matter is very weak, proper calibration of the detector is very, very important. Otherwise, the signal will be lost with the background noise from background radiation. So this calibration is done using a americium source that produces two distinct decays. So there's several connections that can be made here to physics 30 with radioactive decay. Both of these are beta decays, and you can look at what the beta products or beta decay products are. In addition, we look at, in this particular plot, we're looking at the energy and of each event and the number of events that are recorded. So you can look at both what wavelength of EMR would be produced or how much energy would be produced by each of these, as well as the frequency that you'd expect to produce those. This activity has a number of different questions that deal with several different areas of physics, in this case looking at muons and how muons travel through the atmosphere, because they're a source of background radiation for these detectors in SNOLAB. And so in this question, it's a fairly simple conversion from MeVs to kilograms, and just asking students to figure out how many times more massive a muon is than an electron. The next activity looks at the operation of NUSG, and in this case, we're looking at the decay of argon-37 and the beta capture in this case that's used. So like I said, there's several connections that can be made to the physics 30 unit on nuclear decay. Again, I like to put in questions where I ask my students about nature of science questions. So for instance, in this question, which is part of this same activity, students are asked to explain why it might be important to use two different detectors or multiple different detectors to look for dark matter instead of just focusing all of our energies on perfecting one type of detector. Coming up with plausible reasons why there are several different detectors being pursued right now for dark matter research. And Marie-Cécile showed this graphic, I believe, in her part of the talk. And so each of these curves represents a sensitivity of a different detector. They all rely on different physics, and so we can get overlapping evidence for dark matter being detected or not being detected by different detectors, and be fairly confident that it's not simply, say, a quirk of the physics involved in that particular detector if we're seeing it in multiple different detectors. Unfortunately, so far, no dark matter signal has conclusively been detected directly by any experiments. So one of the things I did in developing these resources is take information from published research and try and simplify it a little bit to make it a little bit easier for high school students and high school teachers like myself to understand. This is a plot that shows the probability of interaction between dark matter particles and the detector. Now, the technical term for this is cross-section of a particle. And so what it's showing is how likely a dark matter particle is to interact with one of the particles in the detector. So I've made this relative to the strong nuclear force. So essentially relative to the likelihood of a proton-proton interaction and comparing dark matter interactions to that. And so it varies depending on the mass, but you can see in the plot it's all on the order of around 100 billionth to a trillionth to maybe a little bit less than a trillionth of the interaction probability of a proton-proton collision. Anything above that has essentially been excluded by NUSG. So even though NUSG hasn't detected dark matter directly, it's placed some constraints on what the interaction probability is for dark matter particles, and at the same time also said, for various masses, it can't be interacting more than this. So this has a lot of benefits for future dark matter research because it tells researchers what they need to build in order to look for dark matter. So we need to have either detectors that are very sensitive to low mass WIMPs with slightly higher interaction probabilities, or heavier WIMPs with lower interaction probabilities. And the activity for NUSG actually goes into why why this curve has a shape that it does to a certain extent. The last thing I'll talk about here is some of the other resources that people might find useful. So one of the things Marie-Cécile mentioned is we're trying to connect high school teachers and students with physics researchers and the research that's currently being done. So one of the things that I worked on was looking at researchers both at the U of A and within the McDonald Institute itself, who might be interested in and able to provide expertise in different areas of dark matter research. So as Marie-Cécile said, she's willing to talk with teachers and students, as are members of her research group. And if this is something that you'd be interested in doing, I invite you to look at this database. So you can follow the QR code or the link that'll be provided on the next slide. There's over 25 different researchers from across Canada who have been involved in dark matter research and other research, who are happy to share the results of their research, talk to your students, and maybe give some guidance on the specific physics involved in dark matter research. So in this database, their emails or contact information are provided, as are the research projects they're working on, and kind of a summary of what they've been doing, as well as what I felt were some of the most likely curricular links that their research had to our Physics 20 and Physics 30 courses. And so this is about where I'm going to end my part of the talk. If there are any questions, comments, or even suggestions, please get in touch with us. So the resources are live and are available to be used, but we're still hopefully going to continue adding and modifying them. If there's stuff that you found useful, please let us know. If there's stuff that you would like to see or suggestions you have for these resources, please let me know so we can incorporate them. I'd also invite you guys to take the time to fill out this Google form. Because this isn't a live talk, we really don't have much opportunity for feedback, but if you do have suggestions or comments, please take the time to fill out this short questionnaire to let us know what you thought of the talk and what you might find useful in terms of dark matter physics in your classrooms. And I'll just end by inviting everyone to an in-person discussion with Dr. Pirro. If you had any questions about the physics behind dark matter, Dr. Pirro is more than happy to chat with you about it. If there are any questions about the resources, I'm also going to be available on March 4th at 1 p.m. using Dr. Pirro's Zoom room. You can follow the link provided or just check the QR code. If there's any problems with that, please let me know and I will do my best to troubleshoot it for you. Thanks for taking the time to watch this video, and I hope this was useful for everyone.